So, the first thing we're going to start with in my lesson, my part of the lesson, I guess, is we're going to review some vector addition rules.
Oh.
Yeah, fun stuff, eh? So that was, you guys did that earlier in the month, back in Unit 1. So, what happens, can anybody tell me, if you have a vector facing this way, and then a vector facing the same way, how would you add these together? So you got two vectors facing the exact same way. How would you add these?
What do you mean, how would it? 1 plus 1 plus?
Yeah, like vector addition. Remember vector addition from the beginning of the year?
Oh yeah.
You bring them together.
Tip to tail.
Tip to tail, yes,
Oh,
that's exactly
yeah.
right.
Measure it.
Tip to tail. And they just go, since they're both in the same direction, that's the two things that you're looking for is magnitude and direction. They're both the same direction, so they're both just going to add directly together. And they're going to make like an arrow, one arrow that is the same length as this length arrow, plus this length arrow. Okay, so now, what happens if we have one arrow? I'm going to use a small arrow for this one. What happens if we have one arrow going to the left and one arrow going to the right? How are these ones going to add together?
They cancel each other out.
Should you subtract?
Yeah, you're on the right track for
They
sure.
subtract.
Yeah, they're going to subtract from each other. So they're going the opposite direction. That's the first thing we look for. And then, so which direction is the final vector going to be going in?
It's a bigger one.
Yeah, exactly. Perfect. So they are going to subtract by each other. So imagine that this blue arrow comes in here, and then we're going to get an arrow that's about that long. Does that make sense? Okay, perfect. Now, probably the most complicated one, if you have one arrow going this way, to the left, say, and then you have one arrow going down. Now how do you add those together?
It's the perpendicular thing, like you attach them like that. Tip to tail.
Tip to tail,
Yeah.
perfect. Yeah, exactly. So tip to tail, and then what's your next step? Does anybody know?
Draw a hypotenuse.
Yeah, exactly. And which direction is that hypotenuse going to be in? So, if you have your arrow going this way, and then like you said, we connect them tip to tail.
It's going to be tip to tail, so start from the bottom and then,
Okay, start from here.
yeah, and then go up, and that's where you draw your arrowhead
So which side is my arrowhead on?
on the top.
Up there?
Yeah.
It should be the other one.
That's actually the bottom.
Bottom?
Yeah.
Oh,
Yeah.
okay.
Okay, so for connecting two vectors, it's tip to tail. Then when you draw your final hypotenuse vector, it's actually going to be at the tip of the vector it's closest to. Okay, does that all make sense? Okay, so that's just our review of vector addition. We're going to use some of that's an important concept for what we're working on today, and that is going to be circular motion. Okay. So, circular motion. You guys could probably guess what circular motion is, right? When something's moving in a circle. Okay? So, for example, I'm going to give you guys a circle here. I'm not an artist at all. So, imagine you have an object up here at the top, and it's traveling around in this circular motion. Pretend it's a perfect circle. And it's attached by a string to a center. So I'm holding something, spinning it around, right? At this pause right here, the object is still moving, but we're going to pause time. What direction is the object moving when it's right at this instant? At this instant in time.
What direction?
Yeah. Or which direction, which direction is it moving?
That way. Downwards.
Downwards or You said which way? So I hear downwards and then I hear
That
this way?
Yeah, right at that moment, I think that would.
Yeah, he's exactly right. So right at this moment, I'm actually going to use a different color pen. Actually, I'm going to use these pens. I don't like your pens, Josh.
Sorry, mister.
Right there. So we have our, this is our velocity vector. Okay? So at this instant in time, the velocity is traveling tangential to the circle. Okay? This is called tangential. Tangent to the circle is like straight across the horizon of the circle. Does that make sense?
Yeah.
Good with that? Good with tangential? Okay, so this, we have a tangential velocity. But you said that it was moving down. Why would you think that?
Because when the force of gravity, be working on it as well.
Okay. True, if we have an external force, but we're going to ignore that
Okay.
force for now. We're just going to say it's spinning around.
Mm-hmm.
But, okay, so this ball, obviously it's attached by a string. So when you're spinning it around here, it's moving in this motion. So let's say at some instant in time, it's going to end up here. Right? So, isn't that weird? Because your ball, it wants to go this way, but it ends up going this way. Why is it doing that?
Force of gravity.
Tension maybe?
Yeah, tension. So we're ignoring gravity for now. We're gonna pretend that there's no gravity acting on this, but yes, there is a string, so you have a tension force. And that tension force is bringing it always towards the center. So your tension force here is bringing it towards the center. And we just put F subscript T for force of tension. Okay, so yeah, we got your velocity vector, you have your force of tension. This force of tension in circular motion, that is called our centripetal force. Okay? So the centripetal force in this example with a string spinning around is our force of tension. So, when you have, this is an example of uniform circular motion. So we have a constant velocity, no matter where this object is, its velocity is always going to be the same, just in a different direction. That makes sense, right? So that's called uniform circular motion. Uniform basically means it's a constant speed, okay? So we have a uniform speed throughout the entire circle. It's always moving at the same speed. So that's uniform centripetal motion. Okay, so just as a example, conceptual example, when you're in a car and it's moving around, or you're taking a right turn or a left turn, or you're going an on-off ramp on a freeway, what do you guys feel? Like, what are the forces that you feel? I need to erase this one. So you're coming around, you're going on an on ramp. So say it's like that. So it's kind of like a 3/4 circle here when you're going onto a freeway. What kind of forces do you feel when you go around that on ramp?
You get pushed to the outside.
You get pushed to the outside. Yeah, exactly. So you're going around. Say you're here. You sort of feel like you're getting pushed outside, right? Like you take a turn really, really fast. You feel your body start to turn this way. Your car starts to kind of shift a little bit towards the outside wheels. So actually, what's happening there is you're not really being forced outside. It's your body and the car trying to continue in that tangential velocity. So this is, at this instant, as we explained before, this is the motion that your body is making, right? You're going straight ahead. But what's happening is you're turning, and when you're turning, your body and the car are still trying to go this way, but there's another force that is causing you to turn. And this is another centripetal force. Does anybody know what the force is when you're in a car and you're turning? What is the main force that helps you turn in a car?
Friction,
Between?
the wheels and the road.
Perfect. Exactly. So here, in this case, this is a different example of some centripetal motion where you have a force of friction that is bringing you towards that center point, okay? So, now this is why, can anybody tell me why you would want to have a high force of friction?
So you just slide off if you
Yeah, exactly. Okay, so,
Yeah.
exactly. So you want, with a car, you want a high force of friction so that you do continue on this circular path. Without this high force of friction, your body and the car are going to go this way, and you're going to start sliding towards that tangential velocity, okay? So you want this to be high. So any factors that affect that, you know, wear in your tire, ice, rain, there's a lot of factors that affect that, and, you know, so, yeah. So right now I'm going to do a demo. Okay, so this is just, so I have 3 tennis balls, and I have a bucket. So as you can see, as you can see, there's no glue or anything in the bucket. Tennis balls are going to fall if I tip the bucket upside down, correct? Right? Gravity, right? So, what do you guys think will happen if I start spinning this bucket over, like, this way? What's going to happen?
The balls will stay inside.
The balls will stay right on. Okay. So, I guess that's your hypothesis. We'll test that hypothesis. Ooh, yes. So cool.
Woo. Now let go.
Yeah, let go and worry. All right, so all 3 of the tennis balls stayed in there. Okay? So can anybody tell me why that might have happened? And remember the example with the car, with the velocity. Why would the tennis balls stay in the bucket rather than falling out?
Well, the friction was higher.
It's not friction in this case, though. It would be, so, remember back to the first example where we had the ball and the string? Which force was that?
Tension.
Yeah, tension, okay. So we do have some tension in this metal wire, I guess. So, but remember, the key thing I want you to remember is this velocity. Because this is where, remember with the car, your body and the car, they both wanted to travel in this direction when you were driving. That's why you felt forced to the outside. So relating that, what can you say about the tennis balls in the bucket when I spin it?
They want to go straight, so they hit the side of the bucket.
Yeah, they hit like the side and the back of the bucket. So the tennis balls actually stay in the bucket. I wish I could put like a camera in the bucket to show you where the tennis balls are. But they stay basically right on one side corner of the bucket. Because that's where the velocity is. They're trying to go that way. Because every time I'm swinging the ball, right? I'm swinging from here. It's going up. Now I'm here. It's traveling this way. Right? Does that make sense? That velocity vector. So that's key. You got your velocity vector, and you have your force. In this case, it's tension in the wire of the bucket. All right. So, what if I start spinning this bucket really, really fast? How do you think that affects the centripetal force? The force of tension, I guess. Centripetal force.
Greater, it'll increase.
Yeah, exactly. So the faster I spin this bucket, the easier it is for these balls to stay in there because there's higher force, there's a higher velocity, everything's greater, okay? So what happens if I spun this really slowly?
The ball's also gonna fall.
Yeah, because the centripetal force is
Yes.
lower. It's a lot lower. So, look at that. So you do need. Yep. So. Oh, don't want to put it in front of you. So when you're going around really fast, you have a higher centripetal velocity. Okay. Or you have a higher velocity and a higher centripetal force. Everything's higher. So relating back to our car problem, where we have a car going around the loop, what do you think happens if you have a higher velocity?
Then friction?
You do have higher friction. Or no, sorry, you don't have higher friction. But what happens is you have a higher velocity, so you actually have a greater chance of skidding off, okay? So that's actually why it's better to take a corner really slowly. Does that make sense? So. Oop, drop my arrow. So all of this, you got your velocity, you have your force bringing it inside. That's centripetal motion. So I have a short little video I want to show you on the board. Okay, so this video is just emphasizing the fact that we have all of our, as you travel around the circle, all of the forces are pointing towards the center, okay? So your force vectors are the pink, and your velocity vectors are the green, all right? So every single time the ball hits the side of the circle, you can see where it's traveling, right? And it gets tighter and tighter towards the circle until it's basically is traveling around in a circular motion. So, in this video, okay, I don't need to play again. What we have happening is you have your velocity traveling this way, and then every time it hits a barrier, its velocity changes. Do you guys remember what Newton's first law is? From the first unit?
Something in motion stays in motion?
Yeah. So an object in motion will stay in motion unless acted on by a force, by an external force. So in this example, what this is just emphasizing the fact that in circular motion, the object is traveling in one direction. At that instant in time, it was traveling tangential to the circle. What's happening is it's acted on by a force, and that's why it's changing direction. So that force is your centripetal force. Is this all making sense? So everything always relates back to Newton's laws and of motion and all that stuff. Okay. That's the end of my portion, and now Josh will take over from there.